One thing that's different here than I think maybe it was our warm-up yesterday. Yesterday you could have started by distributing the fraction. And that works fine on the left-hand side, but on the right, when you distribute 5/4 to 2 and you get 10/4 or 5/2, now you do not get an integer there, and that might have tripped you up a little bit. It still would have taken care of itself when you go to multiply by the least common denominator, which I used 12. You could have used 24, 36, any multiple of 12. So what I did was multiply both sides by the 12. I put it over 1 so I could multiply fractions across the top and bottom. And then I only multiplied it by, so when you're doing order of operations, you multiply left to right. So it's this one times this one. That gave me 24/3, which gave me 8. Then I multiply that by the third thing, which was the x minus 3. Right? So if you're multiplying left to right. Same thing on the right-hand side. Let's say you got 12 and you did the fractions and everything, but you forgot to do 12 times this term, this one. That's a procedural misunderstanding. That's an 85. Okay? But if you just did the math wrong when you multiplied by 12, but every other step was right, that's a simple math mistake. That's a 95, as long as your procedure is correct. Does anybody have a specific circumstance that they don't mind sharing in case someone else made that mistake? Then I could talk about it here. Anyone? All right. Put the grade that you feel like you earned on the top, pass those to the back, and then we're going to start our lesson. Yes, ma'am. Talking about interval and set notation for simple inequalities. Later we'll talk about inequalities that aren't so simple, but today they'll be pretty straightforward. Which of these kind of notations have we already talked about since school started? Set, right? And I told you that I was going to say that set notation gets what's. That starts with an S sound. Squiggly wigglies, right? And so this is the lesson where it all becomes clear why I would even introduce such a silly thing to you in the first place. Because today we're learning not only set notation, but something else called interval. And you'll have to remember which one gets the squiggles and which one doesn't. So set notation that we talked about previously was for when we had like individual elements. That equation you just solved in your skill check, x equals -6, if I were to ask you to write that solution set in set notation, you would write squiggly, -6, close squiggly. And that set would have one element in it. And that's how you solve an equation. There's one solution to whatever, a discrete number. However, inequalities is continuous information. And a solution set in an inequality generally has infinitely many solutions, and we represent that with less thans, greater thans, and so forth. So we'll talk today about how to use set notation, yes, but for inequalities, and how to also write that in interval notation. And we're going to start first by just plotting a solution set to an inequality in picture form or graph form. This says plot points with values of at least 1. So give me some number that satisfies that condition. And I'm going to plot it. 3? Yeah? Okay. 3 definitely works. 3 is at least 1. So I'm just going to throw some numbers up here. Okay, 3 works. So I'm going to plot that point. What else works? 1. 1 definitely works. because at least means it can equal 1. What's something that will work between 1 and 3? 2. What's something that would work between 1 and 2? Okay, and I could keep playing that game on and on and on forever, right? For infinity. And the way we show that on a number line is we shade it in, right? We shade in everything between there and there. And in fact, if I need everything at least 1, that means everything greater. I'm going to shade in all the way out to positive infinity. And I'm going to shade in this arrowhead out here to illustrate that. Okay. That is the solution set of all the values that are at least 1. And we are used to seeing it with a closed circle, but I'm introducing you to a new notation today. And I'll explain it more in a little bit. I'm not going to leave you just hanging. But for right now, just trust me. And I want you to write a straight bracket right here. Now, that is a picture representation of the solution set. Here's how you would write that in set notation. Write it down, and then I will explain to you what each piece means. Squiggly wigglies, because it's set notation. Sometimes this is also called set builder notation. That very first X that I wrote down is just me telling the reader that I'm talking about a bunch of X values, and I've called them X. You could use any variable there, M, T, whatever you're talking about. Okay. This vertical bar is not a number, it is a bar, it's a symbol. It stands for such that, and I'm going to write that down in a second, like actual words. Okay, such that. All of the values of X are greater than or equal to 1. So if you were reading this out loud, you would say something like this. The set of all X such that, you say the such that part when you get to the bar, X is greater than or equal to 1. In abstract math, when you're doing lots of proving of things, and there's lots of writing and less computation, it is much more helpful to have symbols like this than to have to write out all of these words, right? So that's why we have symbols for stuff, just to make the writing easier. And so anyone reading it would know what you're talking about. So set notation gets squigglies. And one more time, the set of all X, such that, that's what you say when you get to the bar, X is greater than or equal to 1. Now we're going to say the same thing now, but in interval notation. This is actually my preferred notation because it mirrors what we already have on the number line. So if I was just translating this bracket and that information to interval notation, it would look like this. And I'll explain it more in a minute. Okay, that bracket is the same bracket I had on the number line. Infinity gets a parenthesis. But I also want you to add this other thing. And we've seen this before. What does this stand for? Yeah. X is an element of this interval. So whatever X you happen to be talking about, it's an element of that. So you might say something like X is an element of the interval 1 to infinity. And you might say something like 1 is included or something like that. And I will be picky on the symbols for this unit while it's a skill of the unit. Later on in different units, if we're talking about an element in a domain or range, I might feel comfortable with you just leaving out that part and just giving me the interval, but not this unit. So I will be picky right now. And we're going to take a few notes on when to use brackets and when to use parentheses. So in general, though, the form the way you set up the interval notation, it always opens up with either a parenthesis or a bracket, and that those on the left face that way. The next thing you write is your left endpoint. Okay, or it's the boundary on the left, comma, then your right endpoint, whatever it happens to be. In this case, it happened to be infinity, which you could say technically is not an endpoint. And then it always closes with a parenthesis or a bracket. And parentheses are for when you used to use open circles on the number line, right? So parentheses are used for, or are a replacement for open circles, and these are what we call excluded values, which is why infinity always gets parentheses, because you can never actually reach infinity, therefore you can never actually include it as an endpoint or a boundary. It always gets parentheses. And so, and by the way, one of these is a parenthesis, two is parentheses. We looked it up last year because it was driving my students crazy that I kept saying a parenthesis on the left, and they thought surely that was wrong, but it was not. I mean, I am often wrong, but it's not wrong then. That was a long time ago. You can see I'm still gloating about it. No, I'm not wrong. And so parentheses are for open circles. What do you think I'm going to tell you straight brackets are replacing? Closed circles. And that's for included values. So in the original example of at least one, it could equal 1, and so that's an included value, and that's why we put a straight bracket on it and not a parenthesis. Does anybody need this up anymore? All right. You go and try something. Both of these need two answers. One where you're representing the solution set, which here, it's blue up here, but it's just dark on yours. You need a set notation for that and an interval notation for that, for both of them. So take a minute and just try it out. See what you come up with. Talk about it, talk about it, talk about it. All right. So for the first one, it's kind of like the other ones we already did, where it goes to infinity on one side. Bless you. So set notation gets squiggly wiggly, so I'm going to start with them. And I'm not even going to use x, because you don't have to. I'm just going to use m, but you might have to remind me later that I did that, because I'm going to switch back to x. All m, what does this bar stand for? What words? Such that, okay. All m such that m is greater than or equal to -2. How did I know that I need to put the wiki bar right there under the greater than? What symbol is telling me that? That can be equal to. The straight bracket, right? So that's set notation. Interval notation, you just model from what's already on the number line. So your left endpoint is -2. It has a straight bracket, so that's how you start. Comma, and then your right endpoint, technically it's not an endpoint. It's going on and on forever, so it's infinity. What symbol does infinity get? Parenthesis, right? What am I still missing here? I would circle this as partial credit until I add in the thing that's missing. X is an element of. Or m, sorry. See, I told you I was going to forget. So m is an element of that interval. What's up with this one? How is this one different from the ones we've done before today? What's going on? There's two brackets, right? There's no infinity. And so you might be like, oh, I don't really remember how to write an inequality for that. Well, here's how I think about it. I think about how for the inequality part, the x's in between represents all values in between here. Okay? So it's all the values that are in the middle or in between -3 here and 2 here. That makes sense, right? At least. Now all I have left to figure out is which way the signs are going to go and if they have bars under them. And so here, is x bigger than -3? Yes, right, because it's to the right. And so when the bigger value gets the open mouth, right, because you're like a hungry alligator and you want the bigger value. So it's going to go like this. And then the next question is, does it get the equal bar there? If it's got a parenthesis on it. Nope. So no wiki wiki. Does the 2 get the equal bar? Yes. So it can be equal to, and 2 is bigger than that because 2 is to the right. So it gets that symbol right there. So in set notation, you start with your squiggly wigglies. You say all x values such that x is between -3, sorry, between -3 and 2 and includes 2. Oh, sorry. So that's your set notation. Interval, easy. Just model it after this. Parenthesis, left endpoint is -3, comma, right endpoint is 2, gets a bracket. Don't forget to add your x as an element of symbols. This is, oh yeah, this is like homework numbers 19 to 21. Okay, so far, what we've done is practice the notation. We were already given the number lines and the shading. What we're going to do next is solve an inequality and then go to the number lines and the notation from that. But does anybody need this up anymore first before we do that? All right. So this one. So you've got your inequality. This works just like solving equations. We've been working on that, but with one extra thing that you have to keep in mind. And that's all these words right here are basically saying if you multiply or divide both sides by a negative number, you have to flip the inequality. I'm going to show you a little basic proof about why you have to do that, and you don't have to write this down. In fact, I just want your ears and your eyes. Let's say we have this true statement that 2 is less than 5. We're all agreed that that's true? Okay. I know from our math principles that we're familiar with, if I multiply both sides of that inequality, the truth of it remains the same. So for example, if I multiplied both sides by 3, I'd have 6 on the left and 15 on the right. Is that still true? True, right? But here's what happens if I multiply by a -3 on both sides. I get -6 and -15. And what happened to the truth of the statement? It's no longer true, right? It's not true that -6 is less than -15. -15 is way out there. -6 is here. We know numbers out to the left are smaller. However, to preserve the truth of the original inequality, if I multiply by a negative and flip the sign, then it remains true. And so that's why we have that rule at all, period, in the first place. It's not just to torture you and give you one more thing to remember. So keeping that in mind, I want you to solve this inequality the same way you have been solving equations, but if at any time you find that you're multiplying or dividing by negative, flip your sign. Okay, so take a minute and do that. If you moved your x's to the left, you would have this, -8x is less than 24. And you would have had to divide by -8. And what do you do when you divide by a negative? Flip the sign. So you would have x is greater than -3. I submit to you that we have the exact same answer, right? Which way on both answers is it pointing? To which thing? Like the arrow's pointing to what? Yeah, it's opening to the x on both of them. It opens here, points to -3. This one opens this way to x, points to -3. These are the same thing, right? So either way, I'll take either one. And what this represents is every number, any number you find that's bigger than -3, if you plug it in here, do your math, it'll give you a true statement. That's, okay, there's infinitely many solutions. So greater than -3, throw yourself some numbers up here. Does this -3 get a parenthesis or a bracket? Parenthesis, because it will never be equal to -3. So I put a parenthesis here. So here's my -3, and it has to be greater than, so that's everything to the right. And it says to write it in interval notation. Does that get squiggly wigglies? No, right? Because it's not a set. And so interval notation is the easy one. You just model it after your number line. So I have a parenthesis at -3. It goes off to infinity with a, what does infinity get? Parenthesis, okay? Because it's always considered excluded because you can't actually reach it. And then I need my x as an element of notation. And this is like homework numbers 23 through 27. We will finish this lesson tomorrow. I'm going to pass back your homework and go over the quiz that I didn't get to go over yesterday.